Assalamu alaikum wa rahmatullahi wa barakatuh, and welcome to the VOC, or rather Voice of the Cape Matric Revision Programme. We are streaming live on Facebook as well as YouTube. The subject is physics, and the topic is work, energy, and power. Our guest today is Muntasir Kadri from Intune Tutoring, and he will be conducting the lesson today. Assalamu alaikum, Muntasir.
Wa alaikum salam.
And I hand over to you to proceed.
Okay, shukran so much. Okay, everyone. As per introduction, we'll be covering physics paper one. We'll be specifically looking at work, energy, and power. Right, so this can get a little complicated, especially when you need to alternate between conservative energy and conservative work and non-conservative work. You need to understand the definitions and the differences between the two in order to appropriately solve the problems that you are attempting to solve. So let us go into it and we look at the first problem, and we'll go through a few definitions along the way to make sense of things for you. So in example one, I state here a demolition ball is used by a crane to break the wall of a building. The demolition ball of mass 1,250 kilograms is lifted by the crane to a point R at a height of 5.8 meters above its lowest position in 60 seconds. The state to ignore air friction. So friction is not something we even need to worry about taking into consideration for this problem. Okay, now we can look at this image here. We can see here's the ball. Here's our height of 5.8 meters. The ball follows a trajectory of some angle. And we can see it over here, and it's running, and it's going to crash into the wall with a certain amount of force. And of course, in that energy that's provided from the potential energy that's provided, once it gets to here, it's going to translate into kinetic energy, and the net value of the work done between the kinetic energy and the potential energy will translate into force that will break this wall. Okay, now let us take a look. First, the state define the term power in words. Well, this is fairly simple, right? All you need to do is look at the equation for that, for which power is, and that is just that power is equal to work, right? It's net work over the change in time, right? And just by this equation, we can state that, well, power is therefore the rate, because anything that's over time is called a rate, right? So a rate, right, is anything that's over time. So this can be any value. I mean, if it was velocity, then we'd have velocity over time, then the rate at which velocity changes over time, that's known as acceleration. The rate at which our position changes over time, as you should know, is your velocity. Now for power, it's the rate at which the work changes over time. Right? And that's how we would answer that. Fairly simple. We'll get a mark for stating rate and for stating change in work over change in time. You'll get your 2 marks there. Okay. Now let's look at the next question. It asks us to calculate the average power dissipated by the crane in lifting the demolition ball to point R. So there's no motion involved here. The ball isn't being released. They just want to know what is the power at this instance here. Well, we established that power is equal to the change in work over the change in time, right? So what would the work be over here, or the energy that we would need over here? Well, we know that if it's up here and we have a height and someone's just holding it still, we have something called potential energy. And as we know, potential energy is just mass times the gravitational constant times height. So let's try to pick up the clues with regards to the information that we have. Well, we have our height, and that's 5.8 meters. That's clue one, right? So we can tick height off. We know our gravitational constant is 9.8 meters per second minus 2. And we know that the mass of our ball is equal to 1,250 kilograms. So all we do is we substitute this information into this formula over here. And then we can just go, well, PE is equal to mgh. So we just go 1250. And once again, I know it seems tedious to put in your units, but trust me, it's very important that you do. M dot S minus 2 times 5.8 meters. Right? And that will give us an answer of, where's my calculator? And remember, 1250 times 9.8 times 5.8. That gives me an answer of 71,050 kilograms per meter squared per second minus squared. And this is just 71,050 joules. Right? That's what we get. Now, we've done the first part. We've calculated the potential energy, or the work that's going to need to be put in to calculate the power that we're going to get over here. Okay. Now, let's find out what the average power dissipated is. Let's take a look. So, we can go work, power is equal to change in work over change in time. But for this specific instance, it's just potential energy over change in time. So this is going to give us an answer of 71,050 joules. Our change in time was 60 seconds. And this will give us an answer divided by 60 of 1,184.17 joules per second. And joules per second is the same as watt. No, that's it. It's watts, right? There we go. Now let's check if our answer is correct. Let's double check with the memo. See that we did our calculations correctly. Oops, I did something wrong. Let me just open this up. There we go. Okay. And there we go. 1,184.17 watts. So we were spot on with our calculations. Okay. Now, let us go on to the next question. For some reason, I ended up opening another window. Let me just go back here. Go. Oops. Here we go. Over here. Right. Okay. Now, that was the first question, 5.2. The next question. The demolition ball is released from point R and strikes the wall at the lowest point of its swing. The ball then moves 0.25 meters horizontally into the wall before coming to rest. So there they give us another clue. And that distance here, this delta x, this change in position is 0.25 meters, right? So to move from here to here is 0.25 meters. And that's going to come in handy later on, especially when we're going to have to calculate the force, right? Or we have to use an equation that equates work and force. Now, let us go down. So, let me just clear this off. Now, they stated define the term conservative force. Huh? Well, a conservative force is basically a force where the pathway taken does not affect the change in energy, right? And that in turn won't affect the force. So let's look at the official definition. I'm going to have to go to this other one that I opened up here. And if we look, it should be similar. So a conservative force is a force for which the work done in a moving object between 2 points is independent of the path taken. Right? So your work done is independent of the path taken. That's what a conservative force is. So it doesn't matter what the path is, it's not going to affect the force in the system. Right? There will always be this equivalent exchange where you know the equation that your work is equal to your change in kinetic energy plus your change in potential energy, and that would be your W net. You can also use that same equation for WNC or WC, which is work conservative and work non-conservative. Okay, so that's the official definition for that. Let me just go over here. Right. So now let's see the next question. Open it up here. There we go. The next question is the force which the wall exerts on the ball a conservative or non conservative force? Well, let's look at the scenario. So, by definition, for conservative, the work done is not affected by the path taken. However, in this specific instance, the work done is affected by the path taken, right? It's going to be affected because this is traveling. It's the kinetic energy is different over here as opposed to over here. The potential energy is different over here as opposed to over here. So therefore, the path taken and the change in height and the change in position is going to affect the work which we put in. So therefore, we can easily state that this is a non-conservative force. 5.5. State the energy conversion that takes place during the downward swing of the demolition ball. Well, the energy conversion is that of going from a gravitational potential energy to kinetic energy. That is what the conversion is. And let's just double check. Where did I put this? Here we go. And we can scroll down. And there we go. Gravitational potential energy to kinetic energy. Very simple, very easy to spot. Right? You know immediately once you have a height and you reduce that height. Remember, if you have height, you're working with potential energy. If you don't have height, we are working with kinetic energy. But although kinetic energy and potential energy exist in both, but the reason they're stating there's a conversion is because of course, because potential energy is decreasing and kinetic energy is increasing as our height is decreasing. Now, if we go back here, 5.6, using energy principles, calculate the magnitude of the average force exerted by the exerted on the ball while it moves into the wall. So we need to use first of all energy principles, right? So of course we're going to be using our kinetic energy and our potential energy to calculate the magnitude of the average force. So things to note. We're looking at force, right? And we are looking at energy. Right, so we're looking at EK and EP, kinetic energy and potential energy. Okay, so how do we go about this? Well, let's first identify the relevant equations that we may need to use, and let's also identify the clues that have been given to us. We know that force, we know that this is equal to mass times acceleration, right? But we know that work is equal to force times the change in distance, right? And then, of course, if there is an angle, we need to take the angle into consideration. So we'll say work is equal to net work is equal to force times change in distance times cos theta, depending on the angle and the trajectory of the ball. However, we also know that net work is also equal to, well, guess what? It's equal to EK plus EP, right? Or, as they might put it in your notes, they might just say potential energy is change in U plus change in K. And this translates into mgh final minus mgh initial plus half mv final squared minus half mv initial squared. All right. So Let us now go about this, solving this problem. Okay, so if we take a look at the memo, I don't want to sit too long because we still got another question to go through. So if we take a look at the memo, we get our formulas written out, and now let's see what they have to say. So if we go here, let me just clear this off. So yeah, very important to remember your equations and understand how they work in relation to the conservation of energy. Now, if we scroll down, here we go. So the state marking criteria, any one of the following formula. W net equals the change in kinetic energy, or work non-conservative is equal to the change in kinetic energy plus the change in potential energy. Substitution to calculate the kinetic energy or initial velocity, right? And if we go down over here, right, we can easily make the appropriate calculations. So here we go, and they show, okay, well, let's first solve for the potential energy. And let me actually do this on the notepad. It can get quite a bit busy. I want to actually be more precise with you guys. Let me go back here. Just grab this image and this information. Right. We'll just grab this. We'll add it to current page. That's fine. Just make it a little bit smaller. Move it over here. Let's go to the next thing. And then, of course, we need this piece of information here as well. Right. So this is just me extrapolating all the clues as you would if you were an investigator. And we just try to put them all together and solve the crime. So here we go. Using energy principles, calculate. There we go. We add it to the current page. And now we have everything on one page. And this will make it easy for us to work with. Okay, and shrink that and move it over here. Okay. Now, let's do this. I know this might look daunting, but it really isn't. Just follow these steps and I promise you, you will be fine. Okay. So let's get our information together. So what's the first thing we need to do? We need to calculate the force exerted by the wall. So we got force, right, times by, sorry, we can say work in C is equal to force times the change in displacement cos theta. But this is also equal to the change in potential energy plus the change in kinetic energy. So let's first solve for our change in potential energy. So if we look at change in potential energy, this is equal to mgh final minus mgh initial. Okay. So mass for this is 1,250 kilos times by 9.8 times by the final height, which is just going to be 0, minus, and I need to get some more space, oops, minus 1,250 times by, excuse the way I'm writing this, 9.8 times by the initial, which was 5.8 meters. Right? And now we just go ahead and we solve for this. Let me just check here what the answer is. Right, and they go ahead and they did that. All right, mgHf minus final. Here we go, 0, and we get an answer of negative 71,050 joules. Right, so that's what we did there. Well, we know that change in kinetic energy is equal to negative change in U. So therefore, our kinetic energy is the opposite of that because of energy of conservation. And we find that our kinetic energy is 71,050 joules. Then we can say, well, we know that network is equal to the change in kinetic energy. All right. So then we put that in and we set up our formula, and then they go ahead and they use this kf minus ki. But work is equal to force times change in distance times cos theta. Okay. So now we're going to go ahead and solve this problem. Well, we know that the final kinetic kf, oh, sorry. Yeah, we know that kf is going to be 0, right? Because we're going to use half mv squared. And we know that at the final point, the velocity is 0, right? Because it's crashing into the wall. But at the initial point, the kinetic energy is 71,050, right? As we stated here, it's initial kinetic energy. Well, then we place it into the equation here, and we're gonna get something like this. I'll just make it a little clearer on the screen. We're gonna end up with 0.25 times cos 180. Sorry, this is force. Force is what we're trying to find, is equal to negative 71,050. Well, they asked for the magnitude, so we don't have to place the negative in as they did here in the final answer, because what we're going to do, we just want the magnitude. We don't want direction, right? We just want magnitude. So now we just go 0.25 times cos 180. That's cos 180 is negative 1, so this is negative 0.25. So therefore, F is equal to negative 71,050 joules divided by negative 0.25 meters. Now, if you remember, joules is kilograms per meters per kilograms per meters per second. Right? Sorry, kilograms per meters squared per second. Is it? No, it is. Sorry, it is kilograms per meters per second. Yes. Per meter per second, yeah, which is correct. Kilogram per meter squared per second. There we go. All right, and we're going to divide this by meters, and then we're going to end up with a value of 284,089 newtons, as in the solution here. All right, so that's how you go about it. Fairly simple. Now, let's look at the next problem. And let me just go here. Next problem we need to look at is a roller coaster problem. Okay, I know how people hate these problems. So let's comments. A roller coaster car of mass 200 kilograms with the engine switched off travels along track A, B, C. A, B, C. Right? Which has a rough surface. So this is telling us we are going to use friction. Friction is going to be involved in this problem. As shown in the diagram below, at point A, which is 10 meters above the ground, the speed of the car is 4 meters per second. At point B, which is at a height of h above the ground, the speed of the car is 2 meters per second. During the motion from point A to B, right, 3.4 times 10 to the 3 joules of energy is used to overcome friction. So we had to put in energy to overcome the resistance which is provided by the surface on which the roller coaster car is traveling. They say ignore rotational effects due to the wheels of the car. Okay, so lucky for us, we don't have to take into consideration any rotational dynamics. Now, let us go ahead and attempt to solve this problem. Define the term non-conservative force. Well, we defined conservative force in the previous question, so of course, non-conservative force would therefore be the opposite of that, where the force is, basically the magnitude of the force is dependent on the route or the path on which the object is traveling. Right? So the path is important here in a non-conservative force. 5.2. Well, and it's obvious that this is dependent on the path that it's taking, because friction is on the path and it's affecting the car. So of course it's non-conservative because you have energy being lost. Right? So 5.2. Calculate the change in the kinetic energy of the car after it has traveled from point A to point B. Well, what is kinetic energy? The equation for that is half mv squared. Are we given masses of the cart? Yes, we are, 200 kilograms. We have our initial velocity here, we have our final velocity here, and we can work out the change in kinetic energy quite easily. Well, what is the change in kinetic energy then? Well, if we go over here, change in kinetic energy is basically equal to Kf minus Ki. If we plot this information in the formula, it's half mv final squared minus half mv initial squared. Now, all we do is we substitute this information in, and we just get a clear spot over here. And this is going to be a half times by 200. And our final velocity was 2 meters per second minus a half times 200 times by 4. Now we are going to get a negative answer here, which makes sense because energy has been lost. So it's not conservative, right? So if you go here, 100, and 100 times 2 is 200. Half times 100. Half times 200 is 100. 100 times 4 is 400. And our answer is going to be negative 200 joules. Now, are we correct? Are we on the right track? Well, let's check the memo and see if our answer matches theirs. Okay, I'll scroll down. Right. Oh, see, I made an error. See, I was rushing through. I forgot to put the power of 2 in here. And the power of 2 in here, I forgot to put that in. So that's where my error was. And that's what happens when you rush through questions. You make these kinds of mistakes. So don't make these mistakes. Now, if we look here, we did the exact same thing. The only difference was the power of 2, and we actually get an answer of negative 1,200 joules, which makes sense because we lost energy due to friction. Yeah. Now, let's clear this off. And let us look at the next question, which is 5.3. Use energy principles to calculate the height. So what energy uses height in its equation? Think about it for a second. Well, we did just look at kinetic energy, and we know that the formula for kinetic energy is half mv squared. So what energy is going to use height? Well, that would be potential energy, which is mgh, mass times the gravitational constant times height. Right? So we go ahead and we will use that. So we can say, oh, well, if that's the case, I can say change in my potential energy. Sorry, they use U. Change in potential energy is equal to, well, U final minus U initial, which is essentially mgh final minus mgh initial. Okay, well, now let's substitute some values into this formula. So we can say change in U is equal to 200. Our final height is just h. Right? Our what's the next one? Oh, gravitational constant. I forgot to put that in. 9.8 minus 200 times 9.8, and our initial height is 10. Okay, so what is the value for change in U? Well, remember, we did calculate kinetic energy, right? And if we are conserving anything, but we are not in this problem, then our potential energy should be the opposite of whatever the kinetic energy was. And let us check if that's what they did. Let's see here. Open this up. Right. And 5.3. Oh, sorry. Yes. We lost energy. Okay. So we can actually use this formula over here. WNC equals change in K plus change in U. And that makes sense because we know it's a non-conservative force. Right. So I actually forgot about a piece of information that they did give us. And that was the fact that during the motion from point A to B, 3.5 times 10 to the 3 joules of energy is used to overcome the friction. right? So that's where the energy went with regards to the non-conservative force. Where WNC is equal to 3.4 times 10 to the 3 joules. So we aren't wrong for using this, but this is just one part of the problem, calculating the change in potential energy. But we know that WNC is equal to the change in kinetic energy plus the change in potential energy. Right. So now we have to input our information. We calculated kinetic energy and we're going to add it to potential and set it equal to the energy used to overcome friction, which is WNC. And if we go to the memo, take a look here, we can see that's exactly what's been done. So there are negative 3.5 times 10 to the minus times 10 to the 3 right, joules. And why is it negative? Well, this is the energy that was used. It's not energy that was gained, it's energy that was lost. So therefore, the value is negative. We set it equal to the change in kinetic energy plus the change in potential energy. We calculated the change in kinetic energy to be negative 1,200 joules. Yeah, here they set it to negative. Right, there we go. Once again, energy lost. They added to this over here, which is the change in potential energy. Right, and then they solve for the problem. So there we go. And this takes a bit of rearranging, so we can look at the calculation here. So all they did was they solve for this, right? They actually divided this value by, let me just get my laser pointer over here. They actually divided this value by this. They first moved this over and added it to this. Then once they did that, they will divide it by these two terms over here. And of course, HF minus 10 will be left on its own, and they'll move the 10 over, and then you'll get an answer of 8.88 meters. Right? So that's how they would have gone about this problem. Not too complicated, but just bear in mind what type of problem you are looking at, whether the energy is conservative or non-conservative, and that will help you determine how you're going to go about solving this problem. Now, let's look at the next question. The next question is calculate the power delivered by the engine to move the car from point B to point C, which is now 22 meters over here. So now we're changing. We're not working with A to B, we're working with B to C, and they want us to calculate power. And if you remember, power is equal to work over change in time. Okay, now we'll look at the memo here since we are running a little bit short on time, and we'll make sense of this the best we can. Now, if we scroll down, which let me just double check what question this was. 5.4. Okay, let's go to 5.4. And here we go. And what do they state to us? Well, appropriate formula used. Once again, non-conservative energy is equal to change in kinetic energy plus change in potential energy. Work done by friction. All right, that's another thing we need to take into consideration. Substitution of 209.8, 13, and 12. All right, this has got to do with our potential energy over here. Now let's take a look and see what happens. Well, we put this information in here. The non-conservative energy, we have to say, well, this is equal to the work done by the engine. And if we look at the question, let me just go back here. Calculate the power delivered by the engine to move the car from point B to point C. And if we go back to the memo, that's what they do here. So the work that needs to push the vehicle from point B to C, right, depends on the work put in by the engine and the work required to overcome the force of friction. Right. So we know the work required to overcome the frictional force, but we don't have the work of the engine. So then we're using this formula here. W engine plus WF equals change in kinetic energy plus the change in potential energy. Okay, so we can go here. We can substitute some information in. Well, this is just going to equal half m times vf squared minus v squared is equal to this. All right, lovely. So you'll get 2 marks for that. Now we come to the substitution part. Well, W engine is equal to 50 times 15 times 2 cos 180 degrees. So where do these values come from? Okay, let's take a look here. Scroll up. Right, there we go. There's the average frictional force of 50 newtons. Right, that's what's acting on it. Okay. We're moving at 180 degrees. What else? What other information did they put in there? We got that. What is this? 15? Well, is that the distance that had to be covered? Let's see. Travel for 15 seconds. So that was the time. Right? So what are we looking at here? Let's take a look, see. So this here is our 50 newtons. Let me just double check. 50 newtons. Yes, that's right. This is our 50 newtons. So I'm looking at that over there, right? Just so I can point it out. This is 50 newtons. And this is why you're supposed to put in units. It makes things easier for everyone. And this is 15 seconds, right? And we times it by 2 cos 180 degrees. So what is this 2? This 2 should be distance, but let us double check. Let us double check the distance. Is speed, sorry, 2 meters per second. Okay. So we go back here. And this is our velocity of 2 meters per second minus 1 cos 180 degrees. Okay, so this is force times change in time times change in velocity. And that's times cos 180 degrees. And this equals the work done by friction. That's where this comes from. That's what that is over there. Okay? And this is the formula you need to use. Right? So this is, it's not the most intuitive formula, I'd say. However, if you backtrack and you look at information on the units with regards to energy, this makes a lot of sense, right? Because this is kilograms per meters per second squared times by time times by velocity, right? And that'll actually end up giving us an answer in kilograms per second, whatever the case may be, which is going to give us our joules. And we can take a look. Okay, so you can backtrack, look at the units, and that'll make sense to you. Now, this is going to be equal to 0. So why is this 0 over here? And that is for this. Well, this is for our kinetic energy. It's interesting that they got this to be 0. Why would that be? The velocity over here and the velocity initial, that's fine, right? And then multiply it out, you get 0. It shouldn't be a double 0 value. Our final velocity is going to be 0. Our initial velocity was not. Okay, that's fine. Yeah, so we end up with 0 over here. Plus 200 for the mass, 9.8 meters per second squared for the gravitational constant. We subtract the final height from the initial height, and we find that the work done by the engine is 27,250.20 joules. We then use the equation for the power of engine from the engine is equal to W engine over change in time, right? And then we'll end up with the answer of 1,814.35 watts. And that's how you would go about solving this problem. Right? So that will be us for today's session. If you would like information with regards to the work we looked at today on work, energy, and power, the notes will be available for you online on the website. You can just go to intuitutoring.co.za. You can go to the 3-stroke tab. It'll give you a drop-down box, and you can just go to the VOC subsection there. That'll show you exactly where to access the information. Okay, I hope the session was helpful. Please enjoy the rest of the day. Assalamu alaikum wa rahmatullahi wa barakatuh.
Wa alaikum salam wa rahmatullahi wa barakatuh. And shukran to you, Muntasir. All the best for the rest of the day. And to all our students, all the best for your mock exams, inshallah. From myself, Ganita Kamar, and the guests this afternoon, we bid you farewell. Assalamu alaikum wa rahmatullahi wa barakatuh.